Hello everyone. So my name is Theodoros Marinopoulos. I am part of the Mechanics of Advanced Materials Research Group, and I'm working with Dr. Lee and Professor Silberschmidt. So today I will be talking about mechanical performance for prosthetics, prosthetic sockets, specifically 3D printed ones. I will be following the typical structure for the presentation with a brief introduction about what is the prosthesis and how they work, the methods we used and some results initially. So when we are talking about the prosthesis, we are talking about a device that is supposed to restore the mobility and the independence of the user. And as you can see, there are many parts that constitute this device. The importance of the socket here lies that it is the only part that is a custom product. It needs to be tailored and fitted in the specific user, and it's not like the rest of the parts directly off the shelf. And they are mostly made out of thermoplastics or cured resins, usually reinforced with carbon fibers. Now, this can take significantly long time because twin link needs to be casted initially, and on this twin out of plaster the technicians will build the prosthetic socket, and the delivery time can be anywhere between 3 weeks and 3 months, and it requires a few repetitions and a few extra visits to do the necessary adjustments for the user. And as you can tell, due to the long process, due to the materials, it can be quite expensive, with the cost in delivery at the moment lying anywhere between 1,000 and 5,000, depending on the quality. And lastly, there is a variable comfort level because it's significantly dependent on the skills of the technician and the feedback directly from the patient. So in this study, we're trying to introduce 3D printing in the rehabilitation, so we can reduce both time and cost. We will do some tests to assess if it is feasible to use them and if they are complying under safety regulations. And we will also explore non-destructive numerical alternatives, namely FA models, as you will see later on. So starting with the original socket design, which is obtained directly from the limb geometry, we did some adjustments that it can accommodate for the attaching mechanism to the rest of the prosthesis, and then we developed a few more designs for the same patient. And as you can notice here, the thickness is also increasing at the lower bottom, that is said to be the this is the area that's the load-bearing area. So we are trying to reinforce it manually in a more conventional way, just by adding the material there. And then subsequently the file is sliced and is printed in a desktop 3D printer. In our case, we are using Ultimakers and raised 3D printers. And as you can see, this is a time lapse. The process at the moment of printing a socket, roughly 20 centimeters tall, that is for a children application. It takes roughly 2 days to print. So we are looking for ways to speed this up as well. You can see the day cycle over there. And then to do the tests, we are following some guidelines for testing prosthetic parts, prosthetic components. You can see the graph directly from the standards and how is in the standing position and how it is aligned during the gait. We are performing static loads and we are using the ultimate strength test. And we are specifically looking at the early stage of the gait when the heel touches the ground. And this is the most loaded stance during walking. So to transfer the loads, we have this massive frame within the instrument machine. and we have one plaster limb with the same geometry from the one that we extracted to manufacture the socket, so we can uniformly transfer the loads on the socket. The loading is obviously a compression one, and the loading rates and the levels are as instructed from the standards. Now we are testing until failure, obviously, but we have calculated the requirements for this application to be roughly 4,000 newtons, which is 5 times the weight of the user, especially when running. At the same time, we've developed an Abacus model, a FEA model, performing the static loading, and we are modeling all the components of the part, so we can accommodate for any deflections or bending because of the high loads inside the structure itself. As you can see, all the material parameters are here. We are using beam elements, although they are rendered a little bit bigger so they can be seen. All the beams are beam elements, and 3D pyramid elements are being used for the socket and the plaster. And the whole model is fixed at the point 8 at the bottom, and a vertical load of 8,000 newton is applied from the top, as it will be from the experiment itself. Now, moving to the results, we can see we tested a couple of materials, and we tested 2 designs initially, the original constant wall thickness and the one reinforced with a 4.5 millimeter instead of 3. So you can see that design can affect, can improve the performance, but depending on the material, sometimes it won't even reach the requirements. As you can see here, the blue and the red are from the same set of materials, just 2 different designs. But although they are both PLA, they do fail initially. So here is another graph essentially of the same results. As you can see, we have a massive increase of weight in both cases, but this doesn't necessarily translate in socket strength. It does for the first material, but it's not sufficient enough to be over the requirements that we have set, the safety requirements. So what we did, once we found the satisfactory performing material, we printed an extra thick design, and since all of them performed well, we're trying to see the level that they would fail and if they can safely bear the loads of the users, obviously. What we noticed is that there is not a monotonic behavior in the fracture levels as we would expect. As you can see, the second design reached the 8,000 newtons without failing for any of the 5 specimens tested, whereas the 6 millimeter, that was the most reinforced one, failed, although successfully passing the requirements, still failed. And this could be possible due to manufacturing processes or the 3D printing methodology itself. So, as you can see, the crack is initiated at the distal end of the socket. It's usually where the plaster limb ends and does the design to attach the pyramid is it's changing to accommodate for the gap between limb and the rest of the prosthesis. And we notice constantly a crack interlayer because of the printing. And although we know that for PLA specifically, we don't have the bond between the layers printing is the same as the bulk material properties. This isn't the case for a structure this big. So we've done a few FEA models for all the designs that we compared. As you can see, the stress is decreasing at the area that we are obviously applying the reinforcement. But as you saw experimentally, this doesn't really translate to real life applications. So this is something that will be looked at in the future to accommodate and be more reliable in terms of predicting the actual behavior. And here to the discussion is what we mentioned earlier because of the 3D printing itself. As you can see here, we have the two printing walls outside, and inside there's a different printing pattern, changing the whole structure internally for the socket, whereas comparing to the photo below, we can see that all the paths, all the printing paths are parallel, so this can lead to different internal defects between the two cases, and both cases can be observed in the same socket as well, which makes it even more challenging when we're trying to characterize or assess the performance. So, to conclude, 3D printing on its own, by now there is some promising results. There is the potential of using it, but as we mentioned earlier, we need to take serious consideration about the material. Even the manufacturer can make a significant difference in the performance of the sockets, the performance of the printing, and improvements are necessary in the FEA models in terms of that still we are assuming that 3D printed structures are isotropic, which obviously is not the case, and more adaptive models need to be considered to accommodate for something like that. So, thank you very much.
Thank you. Thank you for your presentation. I saw that you were studying increasing wall thickness. Have you set an upper limit concerning the weight of the prosthetics related to the weight of the user?
Not directly at the moment, because there is no not a standard limit by the traditional manufacturers. Since you have different options between resins and thermoplastics, there isn't a limit from the official manufacturers. So still we haven't considered it. But to go one step further from that, our next step is to try to minimize the weight of even the original socket design. So we're trying to perform a topology optimization and basically removing the excess material from the top that we don't really need it, and concentrate at the bottom that is necessary and stressed already.
Thank you.
Can I ask you what is the normal type of materials that are used in these types of sockets, and if they relate to PLA in a way, or are they very different? Just because it's not my field.
You mean
normal sockets? Not,
and
yeah.
traditional? So for the thermoplastics, it's usually PETG or different types of nylon, which I'm not sure exactly the name, so I won't give that information, not to be wrong. As far for the resins, we know that they are polymeric and usually reinforced with either carbon fiber or fiberglass, but again, the exact details are.
And have you considered evolving from PLA to a type of material such as PETG or a nylon, a reinforced nylon even? I don't know.
So this will be also considered in the next steps. The problem with these materials is that for PLA, it is established that when you are printing, between the layers you have bulk material properties, so the interface between prints doesn't really affect the structure. But this is not the case for the rest of the materials. So when we are trying to use the numerical models, we are trying to have a material as close to homogeneous originally.
I mean,
say ABS extra Jew, because they have looked at my chart.
Mm-hmm.
Yeah, it looks very confusing. Maybe ABS is stiff enough for these complications.
Yeah, that's good.
Nice.
For the future, but yeah, thank you.
can I just advise for you to try then to replace the infill that you have if you have, you mentioned 4 millimeters. So replace the infill with just walls, okay? And then you can work around that to reduce the defects that you showed in between infills and walls. Just use walls and
You have even a better solution.
Yeah.
So just you can use this opportunity for self-promotion.
Exactly. So, so back to the properties of the PLA, that we know that interlayer there's bulk material properties. We managed recently to manufacture a nozzle that actually prints the whole 3 millimeter, 4 millimeter thickness. So what we're trying to do now is print the whole socket with only one pass for each layer and try to manipulate the thickness by the extrusion of this nozzle. So initial results show that it performs better than the original one, and that the time for print is reduced from 2 days to 8 to 9 hours. So this is the direction that we are going in the future.
Yeah, this is so just generally, we have, in Lumber, we have just in-house software which allows to control the printer, so that you can in one go to change the characteristics of the layer. So generally what now, so just Theo has said, this is the way kind of coming back to the typical standard prosthetic when you have only one layer of the solid material. So we are now trying to combine, clearly having the benefits of the digital feature, which can be easily used for personification of the design, and compared to the traditional way where you are still doing like inverse input of your limb and then making this in a more complex way. Okay, yeah, please go. Oh, by the way, don't be afraid. Our lunch is also postponed, so that's why I suggest we are not eating into anybody's lunch yet.
The question was, so you're testing static loads, from what I understood?
Yeah.
On the prosthetic?
Mm-hmm.
Are you also going to test dynamic loading, or is that something that you have to do first?
So, not yet, but there is a plan for it. The case is that for the prosthetic to be certified by the standards, it needs to pass 8 different tests. So we are trying to take it step by step and just check the boxes. So for now we are focusing on the static loading. There is a second condition that applies to different stands of the gate, also in the static loading case. So we are trying to jump on that, and possibly, we have the machine to do that, but we need to take it step by step to have a solid result.
Okay, thank you very much for here.